Okay, thank you, and welcome back to the fifth and final lecture in this series. So you'll recall that in the second half of the last lecture, we returned to the second of the two population models that I had introduced towards the end of the first lecture. So in this population model, there are capital N individuals in the population at all times. Each individual independently acquires mutations at times of a rate mu sub n Poisson process. All mutations are beneficial, and an individual that has j mutations at time t has fitness 1 plus Sn times j minus m of t, where m of t is the average number of mutations of the n individuals in the population at time t. So the parameter Sn indicates the fitness benefit that one gets from each mutation. We say that each individual independently lives for an exponentially distributed time with rate 1. And when an individual dies, we choose an individual at random from the population with probability proportional to fitness to be the parent of the new individual that is born. So fitter individuals are more likely to have offspring, and the offspring inherit all of the parents' mutations. Now, as I indicated last time, we mostly want to focus on understanding this population model when the mutation rate mu sub n is large and the selective advantage Sn that one gets from a mutation is small. And in this case, the fitness of an individual changes over time like a random walk as different mutations appear. And because there are many mutations, each of them having only a small effect on fitness, this random walk should be well approximated by Brownian motion. And so instead of studying the original population model, we're going to study a model that's based on branching Brownian motion. And because fitter particles are more likely to have offspring, we're going to consider branching Brownian motion with an inhomogeneous branching rate. That is, the branching rate will depend on the position of the particle. So here is the branching Brownian motion process that we're going to study. We begin with some configuration of particles on the real line at time 0. And as usual, we think of the position of the particle as representing the fitness of an individual in the population. We assume that particles move according to one-dimensional Brownian motion with a drift to the left of rho. We're going to say that each particle dies at rate 1, and a particle located at x splits into two particles at rate 1 plus beta times x. So particles with higher fitness are more likely to branch. Now, when x is less than -1 over beta, we can't have the birth rate being negative. So we'll set the birth rate to be 0, and we will increase the death rate so that the difference between the birth rate and the death rate is always exactly beta times x. In fact, as long as the difference between the birth rate and the death rate is exactly beta times x, there's actually quite a bit of flexibility in the exact choices of the birth rate and the death rate. All we really need is that the death rate is bounded below by some positive constant c, and the birth rate is bounded above by some positive constant for x less than or equal to 1 over beta. Some of our results also require that the birth rate be non-decreasing and the death rate be non-increasing, and those are natural assumptions given that we are interpreting the position of the particle as representing fitness. Now, we want to use this branching Brownian motion process to approximate a population of fixed size. And so we're going to choose the parameters rho and beta, as well as the initial configuration of particles in such a way that the number of particles remains reasonably stable over time. And the results that I state for this model will be based on two joint papers, one with Matt Roberts and one with Jiaqi Liu. Now, before we delve into that model, I want to mention briefly some other related work. So as I mentioned last time, this model was studied in depth by Neher and Halschek, and most of the results that I'm going to present were obtained non-rigorously in their paper. Also, Erin Beckman, in her PhD thesis, also considered branching Brownian motion with an inhomogeneous branching rate, and she was also motivated by potential applications to populations involving selection. Her model differed in two ways. One, she was considering a system in which the number of particles is always exactly fixed, which is harder to study. And she was also looking at the process on a shorter time scale than what we're mostly going to consider in this lecture. Some researchers have also considered branching Brownian motion in which the branching rate is a periodic function of the position of the particle. In this 2016 paper, the authors showed that this can lead to pulsating traveling wave solutions. Lebetsky, Thornet, and Zaitouni then obtained some results about the location of the rightmost particle, and Ren, Song, and Yang recently studied the additive and derivative martingales for that process. In 2009, John Harris and Simon Harris considered branching Brownian motion in which there is no drift, there are no deaths, and a particle at x branches at a rate given by a constant times the absolute value of x to the power rho. And they show that if we denote by r of t the position of the rightmost particle at time t, then for p between 0 and 2, the rightmost particle at time t grows like t to the power 2 over 2 minus rho. If p is equal to 2, the position of the rightmost particle grows exponentially fast. And if p is strictly larger than 2, then the process actually explodes in finite time, because the particles, as the particles get further to the right, they keep wanting to branch faster and faster. Later, Beresticki, Brunet, Harris, and Roberts obtained some sharper results for this process, particularly concerning the number of particles in different regions, and their proofs were based on large deviations techniques. Now, I want to summarize or look into at this point what these large deviations methods say about the behavior of our process. It turns out that the large deviations methods will not be sharp enough to lead to rigorous proofs of our results. However, they will give us very useful heuristics about how our process behaves. So the starting point for these large deviations heuristics is Schilder's theorem for Brownian motion, which I've stated here in a rather imprecise form. So let's say we have some function f, which maps the interval from 0 to t to the real line. And then the probability that Brownian motion with a drift of negative rho started from f of 0, stays close to the function f until time t, is approximately given by the expectation of this integral here. Now, for branching Brownian motion, what we would like to approximate is the expected number of particles such that the ancestor of the particle stays close to this function f. And the many-to-one lemma tells us that we can calculate this by starting with the particle, starting with the probability that one Brownian particle stays close to the function f, and then multiplying it by a factor that accounts for the branching. And that factor in this case is the exponential of the integral from 0 to t of the difference between the birth rate and the death rate for the particle at time u. And for a particle that's tracking close to the function f, that's going to be beta times f of u. Now, the actual number of particles that stay close to this trajectory f should be reasonably close to the expected number as long as this integral up to time little t is non-negative for all little t between 0 and capital T. If this integral goes negative at some point, then most likely no particles will be able to follow the trajectory past that point, and therefore the actual number of particles that follow the trajectory will most likely be 0, even if the expected number is large. Let's consider the constant function where f of u is equal to rho squared over 2 beta for all u between 0 and t. So then this integrand is always equal to 0. Let's suppose then we start out with one particle near rho squared over 2 beta. Now, one thing that could happen is that the descendants of that particle could just quickly die out. And the large deviations heuristics don't really capture that very well. But assuming that the particles don't just quickly die out, what this tells us is that we would expect the number of particles close to rho squared over 2 beta to stay roughly a constant, or to stay order 1 over time. Now, if we had put that initial particle a little bit above rho squared over beta, then the number of particles staying close to that level would increase exponentially over time, because the branching would dominate the drift. On the other hand, if we had put that initial particle a little bit below rho squared over beta, then this integrand would have been negative and no particles could have stayed close to that level. And so starting with one particle near rho squared over 2 beta seems like about right if we want to study a population whose size is going to be reasonably stable over time. So let's suppose we start with one particle at rho squared over 2 beta. And then if the process doesn't quickly die out, the number of particles that are near y at time t should be roughly given by the exponential of this integral, where the function fy is chosen to maximize the integral, subject to the conditions that the function starts at rho squared over 2 beta, ends at y, and the integral up to time little t is non-negative for all little t between 0 and capital T. And this is just because large deviations heuristics tell us that most particles that are near y at time t should follow a trajectory that's very close to the optimal one. And we can actually solve this optimization problem. We can calculate the function f sub y explicitly, we can evaluate that integral, and that leads us to the result that if t is sufficiently large, then the number of particles near y should be approximately e to the g of y, where g of y is given by this expression here. So here again is that expression for g of y. One can check that g prime of 0 is 0. So the function g is maximized at 0, and that tells us that most of the particles are going to land close to the origin. We can also compute the second derivative of the function g at 0 to be minus beta over rho. And that's now suggesting that the distribution of the particles at time t should be approximately Gaussian, with a mean of 0 and a variance of rho over beta. And that idea that the distribution of the locations of particles should be approximately Gaussian appears in the biology and physics literature, as I mentioned last time. Now, one can also use asymptotics for the Airy function to see that that e to the g of y is approximately given by this exponential times this Airy function. And so this tells us that if we look a little bit beyond a small neighborhood of the origin, then the shape of the number of particles located at y is well described by the Airy function. And that was predicted in the work of Simring, Levine, and Kessler, as well as in the paper of Neher and Halaschek. And then one other thing to mention about the function g is that g of y is 0 if y is equal to rho squared over 2 beta or minus 5 rho squared over 8 beta. And that suggests that we would expect to find the rightmost particle near rho squared over 2 beta and the leftmost particle, the particle with lowest fitness, near minus 5 rho squared over 8 beta. Now we can also get some insight by looking at the trajectory that particles typically follow. So a particle that is near y at time t should follow close to this trajectory f sub y. And the function f sub y is given by this formula here. So what that is saying is that the ancestor of the particle that's near y at time t should stay close to rho squared over 2 beta until time capital T minus little t of y, at which time the ancestor starts to move closer to y following this quadratic function. And this gives us some useful information about the right scale on which to think about this process. We again see that the fittest particles should be located near rho squared over 2 beta. And also you can see from this expression for t of y that a particle that's close to the origin at time t should be descended from ancestors that are near the right edge, that are near rho squared over 2 beta at time rho over beta. So rho over beta turns out to be the natural time scale on which we want to study this process. The large deviations heuristics also tell us something about the assumptions that we should need on the parameters rho and beta. So we've seen that the empirical distribution of the locations of the particles after a long time should be approximately Gaussian with a standard deviation of the square root of rho over beta. So most particles should be within order the square root of rho over beta of the origin. And for these heuristics to make sense, that needs to be much smaller than the location of the fittest particles, which can be found near rho squared over 2 beta. And so that turns out to be equivalent to the condition that rho cubed is much larger than beta. Also, we want to be thinking about weak selection, so that beta times x, which is the difference between the birth rate and the death rate for a particle at x, that should be small even for the fittest particles located at rho squared over 2 beta. And that leads to the condition that the parameter rho should be very small. So these large deviations heuristics give us a good sense of how this process should behave. However, to obtain rigorous results for this process, we need to do the same kinds of truncated moment calculations that we've been making before. So what we're going to do is to fix some large positive number L, and we're going to kill particles when they reach the level L. And let's let QTL of xy be the density for the process when particles are killed at L. And as before, that means that if we start from one particle at x, then the expected number of particles in some set A at time t can be obtained by integrating QTL of xy over the set A. So to make these calculations, we need to be able to find, or at least estimate, this density. Kolmogorov's forward equations tell us that the density should satisfy this partial differential equation here. If we just had the first term on the right-hand side, this would be the heat equation, which the density of Brownian motion would satisfy. But we also need to add this term to include the drift of minus rho. And then this last term accounts for the branching, because the difference between the birth rate and the death rate for a particle at y is given by beta times y. Now, much like we did for branching Brownian motion in a strip, we can solve this partial differential equation using spectral methods. So we can look for solutions of the form e to the lambda t times h of y, and one can then just check that h of y would have to satisfy this second order differential equation here. And h needs to be 0 at the boundary L, and also h of y should tend to 0 as y tends to minus infinity. Because of this y times h of y term that appears, this is actually a simple transformation of Airy's differential equation, and the solutions can be expressed in terms of Airy functions. So the solutions that we get take the form e to the minus rho y times phi n of y, where phi n of y can be expressed in terms of the Airy function. Here, these numbers gamma n are the zeros of the Airy function, which all lie on the negative real line. So the density QTL of xy can be written as a linear combination of these functions e to the minus rho y times phi n of y, which in turn can be expressed in terms of the Airy functions. Now, we still need to choose these constants a sub n in such a way that the density will converge to the unit mass at x, that is the location of the initial particle, as t goes to 0. And one can do this in basically the same way that we did for branching Brownian motion in a strip. And that leads to this formula here for QTL of xy. And this formula previously appeared in this paper of Salminen. So basically, we can write the density QTL of xy as an eigenfunction expansion involving these Airy functions. Now, we're going to choose L to be rho squared over 2 beta minus 2 beta to the minus 1/3 times gamma 1. So that's the level at which we're going to kill particles. And we're killing particles at this level so that when n equals 1, this exponential term here vanishes. If we had killed particles at a higher level, then the expected number of particles would grow exponentially and the truncation argument would fail. If we had chosen particles at a lower level, then too many particles would hit the boundary and the process in the long run would die out. So this is the level at which we want to kill particles. Recall that we noted earlier that we expect to find the rightmost particles close to rho squared over 2 beta. And so what we're doing here is we're killing particles when they get just a little bit above that level, remembering that gamma 1 is negative. Now, if t is large, the n equals 1 term will dominate this sum because the other terms are going to decay exponentially, and therefore we can approximate the density function by the leading term to get this much simpler expression or the simpler approximation for QTL of xy. So I want to make a couple of observations related to this density formula, or this approximation to the density formula. So let's let n of t be the number of particles at time t, and we'll let x1 of t, x2 of t, and so on be the positions of the particles at time t. Notice that the density is proportional to e to the row x times this area function. So that's saying that if we have a particle located at x, then e to the row x times phi1 of x is what will predict how many descendants that particle will have a long time into the future. And so if we define z of t to be this sum here, where a particle at x contributes e to the row x times this area function to the sum, that turns out to be a natural measure of the size of the process at time t. And in fact, if we kill particles when they reach L, this process z is actually a martingale. And it turns out to be the particles that are within order beta to the -1/3 of L that contribute the most to z of t. Those are the particles that are going to have the biggest impact on the evolution of the population far into the future. Notice also that the density is proportional to e to the minus rho y times this area function. And therefore, we expect that the density of particles near y should be roughly proportional to this expression here, which, as we saw earlier, is well approximated by e to the g of y, where g of y was the function that we obtained from the large deviations calculation. So our basic strategy for studying this process is the following. So we first want to study the particles that are very close to L. These are the fittest particles that are going to have the biggest impact on the process far into the future. And to study these particles, we're going to consider the process in which particles are killed when they reach L. So we have to show that particles are not killed at L too frequently, so that the truncation, yes.
Yeah, excuse me, Jason. Could you please recall? So beta to the 1/3 is much smaller than rho, right? That was.
Beta to the 1/3 is much smaller than rho. That's correct. Yes.
Yes. Okay. And okay. And rho is also small, right?
And rho is also small. Yes. Rho is small, and beta to the 1/3 is even smaller. Of course, beta to the -1/3 then is somewhat large, but not nearly as large as L.
Right. Okay. Thanks.
Okay. Yeah. So we want to show first that particles do not reach L too frequently, so that the truncation is not having a severe effect on the behavior of the process. We use first moment calculations to show that the density of particles near y should be roughly proportional to e to the minus rho y times this area function. And then we use second moment bounds to control the fluctuations. And that will allow us to see that the configuration of particles close to L stays relatively stable over time. Now, most particles, however, are not close to L. So to study the configuration of particles near y after a large time t, we recall from the large deviations heuristics that particles that are close to y at time t are most likely descended from ancestors that are close to L at time t minus little t of y. And those ancestors should have been in this relatively stable configuration. And so what we do is to start from that stable configuration of particles at time capital T minus little t of y, and then use additional first and second moment estimates to show that the number of particles near y is highly concentrated around its mean. So we're now ready to start to state our results. And I first want to state the assumptions that we need on the parameters and on the initial configuration. So to state a limit theorem, we need to be considering a sequence of branching Brownian motion processes, which is indexed by n. We'll assume that rho cubed over beta is going to infinity, and we'll assume that rho by itself is going to 0. Those are the assumptions on the parameters that we saw would be necessary from the large deviations heuristics. Now we'll also need some assumptions on the initial configuration of particles. We'll assume that Zn of 0, that's our measure of the size of the process at time 0, is of the order beta to the 1/3 over rho cubed times e to the rho times L. That's just going to guarantee that the process is of the right size to behave in the way that we claim. And then we need this more technical assumption that if we define this quantity yn of t such that a particle located at x contributes e to the rho times x, then rho squared times e to the minus rho l times yn of 0 converges in probability to 0. So what that's doing is it's ensuring that the configuration of particles a long time into the future is not dominated by the descendants of a small number of particles at time 0. So there are many particles at time 0 that are contributing to the process in the long run. So here's our first theorem regarding the Gaussian shape for the configuration of particles. And this comes from joint work with Matt Roberts. So for any positive time t, we can define this random probability measure zeta n of t. And so for each particle located at x, we will place a unit mass at the location x times the square root of beta over rho. And then we divide by the total number of particles at time t to get a probability measure. So zeta n of t represents the empirical distribution of the particles at time t scaled in space. Now we'll let Tn be a times rho over beta, where a is bigger than 1. And then as n goes to infinity, these probability measures psi n of Tn converge in distribution to the standard normal distribution. So the previous result tells us that in the long run, the empirical distribution of the particle locations is approximately normal with a mean of 0 and a variance of rho over beta. Now, at first glance, that may seem a little bit different from the conjecture that I mentioned in the previous lecture, which is that the fitness distribution should evolve over time like a Gaussian traveling wave. But this turns out just to be a matter of how we interpret the drift, because our model is basically equivalent to a model in which there is no drift, but at time t, the difference between the birth rate and the death rate is beta times x minus rho times t. And in this model, we can see that the distribution of the locations of the particles is evolving forward at a speed rho. And so we can interpret the drift in our model as being the speed at which the Gaussian traveling wave advances. Mathematically, it was convenient to subtract off the drift so that the birth rates and the death rates would depend only on the position of the particle and not on time. But nevertheless, this other model is basically equivalent. And so we can interpret that drift rho as being the speed of the Gaussian traveling wave. And with this interpretation, we can see that our results are consistent with Fisher's fundamental theorem of natural selection. So in 1930, Fisher postulated that the rate at which the fitness of a population increases is the variance of the distribution of the fitnesses of the individuals in the population. So in our model, 1 unit of space corresponds to a fitness difference of beta. And so the rate at which fitness increases in our model is beta times rho. Likewise, the variance of the fitness distribution in our model is beta squared times the empirical distribution of the particle locations, which is rho over beta. And once again, we get beta times rho. Now, this still may seem like cheating because we started with rho as one of the parameters in our model. However, one can calculate using our model that in the long run, the number of particles should be of the order beta to the 1/3 over rho cubed times this exponential factor. And that establishes a relationship among rho, beta, and n. Now, mathematically, it was most convenient to start with rho and beta and then solve for the number of particles n that would be sustained in equilibrium. But one could also start with n and with the parameter beta that measures the strength of selection, and then solve for the drift rho that determines the speed at which the fitness distribution advances over time. Now, the previous result indicates that most particles should be within a distance of order the square root of rho over beta of the origin. However, we are also interested in understanding very well the configuration of particles that are very close to L, because those are the particles that have the most impact on how the population is going to evolve far into the future. And we have a theorem also about the configuration of particles that are within a distance of the order beta to the -1/3 of L. So we make the same assumptions on the parameters and the initial conditions that we had before. But this time, for each time t, we will define this random probability measure psi n of t. So for a particle located at x, we will assign a mass of e to the rho times x. So particles that are fitter, particles with higher fitness are going to be assigned more mass. And then we will place that particle at 2 beta to the 1/3 times L minus x. So the further below L the particle is located, the further above 0 the mass is placed. We'll then let T sub n be A times rho over beta, where A is positive. And then these these random probability measures psi n of Tn converge as n goes to infinity to the probability distribution nu on the positive real line, whose density is given by the portion of the Airy function to the right of the largest 0. So basically, the Airy function is describing the configuration of the fittest individuals in the population. So far we have a result about the bulk of the particles, which are close to the origin, as well as the fittest particles, which are close to the right edge. However, there are also many particles in between these locations, as well as particles to the left of the origin. So ideally, we would like to have a fuller understanding of the configuration of particles, and that's what we were able to achieve in my more recent preprint with Jiaqi Liu. So let's let Ln star be rho squared over 2 beta, which is roughly where we expect to find the fittest particles, and Ln dagger be -5 rho squared over 8 beta, which is where the least fit particles should be located. And we'll let nt of A be the number of particles in the set A at time t. So now we want to make the same 3 assumptions that we've made before. And we now want to consider a sequence of intervals I sub n. The length of these intervals needs to be much larger than 1. And then these other two conditions just ensure that the intervals have enough of an overlap with the interval from Ln dagger to Ln star, which is where the particles are actually located. And now this theorem gives us a rather precise result about the number of particles in the interval I sub n. It says that the number of particles in the interval I sub n divided by this expression on the right-hand side converges in probability to 1. Now this expression on the right-hand side is proportional to the integral over the interval In of this function here. And so that's telling us that e to the gn of y multiplied by this small correction of 1 over the square root of 2 pi times Tn of y is approximating the density of particles near y, just as the large deviations heuristics predicted that it would. Now, this formula is also proportional to the size of the process Zn, not at time Tn, but at time Tn minus Tn of Zn. Now, Zn is the point in the interval that's closest to the origin. So that's the point where we would expect to find most of the, near where we would expect to find most of the particles. And so the reason that we get this factor appearing is that particles located near Zn at time Tn are going to be descended from ancestors that were close to the right edge at this somewhat earlier time. Now we also have a theorem about where the rightmost and leftmost particles are located. So let's let Rn of t be the position of the rightmost particle at time t, and we'll let Gn of t be the position of the leftmost particle at time t. Recall that we had defined this quantity L, which was just a little bit above Ln star, remembering that gamma 1 is negative. And I'm now going to define L bar to be just a little bit below Ln dagger. And then this theorem says that that for a time which is of order rho over beta, the location of the rightmost particle at that time is going to be very close to Ln with high probability. And if we're willing to wait long enough for the particles that are near the right edge at time 0 to have descendants that make their way all the way to the left edge, then the location of the leftmost particle is, with high probability, very close to ln bar. Now, I want to comment on how we prove this result, specifically for the location of the rightmost particle, because it involves an idea that's different from the ideas that we've discussed up to this point. So let's step back and just consider an ordinary Bienemé-Galton-Watson process whose offspring distribution has a mean of 1 plus epsilon. So it's supercritical, but it's very close to being critical. Now, if we start with just one particle at time 0, the probability that this process survives forever is going to be of order epsilon. Suppose the number of particles at time 0 is much larger than 1 over epsilon. Well, then this is going to behave very much like a supercritical branching process. There are going to be many particles at time 0 that will have descendants that survive forever. And so the number of particles is going to increase steadily over time and stay very close to its expectation. That's just a consequence of the law of large numbers. However, if the number of particles at time 0 is much smaller than 1 over epsilon, then we're barely going to notice this epsilon here, and the process is going to behave very much like a critical branching process. In particular, with probability close to 1, the process is going to die out. So now let's go back to considering our model, and suppose we have a particle at L sub n. Well, we know that the difference between the birth rate and the death rate for this particle is going to be equal to beta times L. And because L is approximately rho squared over 2 beta, this is going to be approximately rho squared over 2. And because rho is going to 0, we need to think of this as being something small, like this epsilon here. Now, if t is of the order rho over beta, we can calculate that the number of particles that reach L by time Tn is going to be of the order 1 over rho squared. And if we focus only on the particles that reach L relatively close to time Tn, that's going to be even much smaller than 1 over rho squared. Now, 1 over rho squared is like 1 over epsilon here. And so we need to think of these particles that reach L close to time Tn as behaving more like a critical branching process. So here is a theorem that, that pertains to branching Brownian motion when the branching is critical. And this goes back to Sawyer and Fleischmann in 1979. So let's consider branching Brownian motion started from one particle at the origin, in which each particle dies at rate 1, and each particle splits into 2 particles at rate 1. So the number of particles is just evolving like a critical branching process, and in particular, this process is guaranteed eventually to die out. Now, if we let capital M be the maximum position that any particle ever attains, then they show that the probability that M is bigger than X is asymptotically 6 over X squared as X tends to infinity. So this tells us in particular that if we start with n particles at time 0 rather than 1, then the maximum position that any particle ever attains should be of the order the square root of n. And we can actually use this result to show that for our process, no particle that's alive at time Tn is more than a distance little o of 1 over root n above Ln. So here, this little o of 1 over root n is the square root of this 1 over rho squared here. I also want to comment briefly on the genealogy of the population. Neher and Halischek gave a detailed, non-rigorous argument that the genealogy of this population can be described by the Bolthausen-Snettmann coalescent. We have not yet managed to prove this result rigorously, but we do believe that this can be done, most likely following the same ideas that were used in the case of branching Brownian motion with absorption. And the idea, as before, is that the particles that drift unusually far to the right and get close to the level L may produce a sufficiently large number of offspring, that those offspring eventually constitute a substantial fraction of the entire population. And as a result, that could lead to multiple mergers of ancestral lines when we follow ancestral lines backwards in time. And to give just a brief calculation to support this idea, one can calculate that particles reach the level L at the rate beta over rho cubed. Now, because the difference between the birth rate and the death rate for a particle at L is approximately rho squared over 2, we see that a particle that reaches L has probability approximately rho squared over 2 to have many surviving offspring, as opposed to just quickly dying out. And so if we multiply beta over rho cubed by rho squared, we see that the rate of events in which we see a large jump in the number of particles should be of order beta over rho. And that tells us that multiple merger events should be occurring on the relevant time scale of order rho over beta. So finally, I want to go back and think about what these results for branching Brownian motion with an inhomogeneous branching rate might tell us about the original population model that we stated at the beginning of the lecture. Now, one challenge is to match up the parameters. So in the original population model, so remember that individuals acquire mutations at times of a rate mu Poisson process. So in one time unit, each individual gets a Poisson mu number of mutations, and each mutation increases the individual's fitness by S. And so this tells us that the variance of the change in fitness in one time unit is given by S squared times mu. Now, in branching Brownian motion, because one time unit corresponds to beta units of fitness, the variance of the change in fitness from one Brownian particle in one time unit is beta squared. And this tells us that the parameter beta in branching Brownian motion corresponds to S times the square root of mu in the original population model. Also, we saw that the number of particles n in the branching Brownian motion model is roughly given by this expression here. And so one can then do some algebra to see that rho cubed is approximately 2 beta times the log of n cubed times beta squared. And this means that the crucial assumption that rho cubed over beta is going to infinity reduces itself to the condition that the log of n cubed beta squared is going to infinity, which is equivalent to the condition that n cubed times s squared times mu is going to infinity. Another condition that we need is that the random walk should be well approximated by Brownian motion. And I believe that this approximation should be valid as long as many mutations occur on the smallest time scale that's relevant for the branching Brownian motion process, which is the time scale of order 1 over rho squared. And so this means that we should need the mutation rate mu to be much larger than rho squared. And translating this, one ends up, one sees that this translates into the condition that mu over s should be much larger than the log of n cubed s squared mu. And it turns out that both of these conditions have appeared in the biology literature or the physics literature, and in particular in this paper of Melissa, Good, Fisher, and Desai. But when these conditions are satisfied, we do believe that our results for branching Brownian motion with an inhomogeneous branching rate should carry over in some form to the original population model. And furthermore, because the convergence of random walk to Brownian motion is quite robust, requiring only independence and a second moment condition, we believe that the results for branching Brownian motion should be able to carry over to a fairly large class of population models. In particular, the results should hold even when the mutations are deleterious, or even when the change in fitness resulting from a mutation is random. So what kinds of implications could this have? Well, we saw that for branching Brownian motion with an inhomogeneous branching rate, the fitness of the population was increasing at a rate of beta times rho. This is the kind of a result that one should be able to translate back to the individual-based population model. And in a case of a population model where individuals acquire beneficial mutations, such as the ones that we've been looking at, this should tell us something about the rate of adaptation, or the rate at which individuals acquire new mutations in the model. For a population model in which the mutations are deleterious, this could give us some insight into the speed of a phenomenon known as Muller's ratchet, which is that the fitness of the overall population can decrease because on rare occasions, even a deleterious mutation will get lucky and spread to the entire population. In models that involve both beneficial and deleterious mutations, one could get some insight into the question of mutation selection balance. And that's the question of what proportion of the mutations need to be beneficial in order for the population to sustain its current fitness level. So it appears that trying to establish rigorously some of these results in the case of population models of fixed size could be a fruitful area for future work. However, there are significant technical challenges. First, one would have to work with random walks rather than Brownian motion. That's probably manageable because there are already many papers which take results for branching Brownian motion and carry them over to the case of branching random walk. But more importantly, one loses a lot of independence when considering a population of a fixed size rather than allowing the individuals to branch independently. And this makes calculations much more challenging. Also, we are likely to see some different behavior in the two models. For example, in the branching Brownian motion model, we believe there are occasionally events in which the number of particles increases very rapidly because the descendants of a particle that reached the level L are ready to start to take over the population. Now, in a model of a population with fixed size, that means there would need to be a large number of nearly simultaneous deaths in order to make room for those individuals. And it's not entirely clear, at least to me at this point, what kind of effect those death events would have on the overall behavior of the population. So I don't think it's in any sense trivial to rigorously extend these results to the case of population models with a fixed size n, but I do hope that eventually progress will be made in that direction. So finally, I just want to summarize what we've covered in these lectures. We've seen that for many classical population models, the genealogy of the population can be described by the classical Kingman's coalescent with only pairwise mergers of ancestral lines. But for populations with large family sizes, the genealogy may be described by a coalescent with multiple mergers. In particular, if individuals have k or more offspring with a probability proportional to k to the minus alpha, the genealogy is best described by a beta coalescent. We introduced two population models involving selection. In the first population model, individuals were killed when their fitness gets to be too low. And we argued that this population model could be approximated reasonably well by branching Brownian motion with absorption. And in the second population model, individuals with higher fitness are more likely to have offspring. And we approximated this population model by using branching Brownian motion with an inhomogeneous branching rate. So in both of these models, we were able to use the tools that are available for studying branching Brownian motion to get some rather precise information about how the population evolves over time. In particular, in both models, we're able to understand very well the fitness distribution of the population. In model 1, we saw that most particles were located near the barrier at the origin. In model 2, we saw that the bulk of the fitness distribution is Gaussian, but the fitness distribution further out on the tails can be described better using the Airy function. We've also seen that the Bolthausen-Schnittmann coalescent often describes the genealogy of populations undergoing selection. For branching Brownian motion with absorption, this was first observed by Brunet, Derrida, Mueller, and Mounier, and was later proved rigorously in some work with Julian and Nathaniel Beresticki. In the second model, in the case of strong selection, the Bolthausen-Schnittmann genealogy was first observed by Desai, Wolczak, and Fisher, and I was able to establish this in a mathematically rigorous way a few years later. In the case of weak selection, when the mutation rates are very fast, this result was obtained by using non-rigorous methods by Neher and Halischek. I believe that it's likely to follow rigorously from ideas in my paper with Matt Roberts, but up to this point, that has not been done. So based on these results, I think it's reasonable to consider the Bolthausen-Schnittmann coalescent to be a kind of universal object, which which describes the genealogy of populations undergoing selection in a fairly wide range of circumstances. Nevertheless, in recent years, evidence has been emerging that other beta coalescents also describe the genealogy of populations undergoing selection in some circumstances, especially when we have these so-called semi-pushed waves. That's an idea that goes back to the work of Birzu, Halaschek, and Korolev. Recently, Cortinez and Malin, as well as Tournier, have started to establish some preliminary rigorous results in this direction, but this remains an active area of current and future work. And I will stop there. Thank you for listening until the end.
Do we have any questions for Jason?
So thank you very much. I have a question about the perspective that you mentioned at the very end. I understood that there is one direction, which is to replace the Brownian motion by a jump due to the fact that the fitness has the distribution of fitness effects is given according to some kernel. And another direction, which is having a fixed size of the population. And I didn't get if these two are coupled or if you can follow one direction and one other. Are there two different things, or
okay, so
are they linked together?
Yeah, so one of the things you mentioned was a fixed size of the population, and the other was allowing the change in fitness from a mutation to be a jump. Yeah, so I was sort of thinking of the two together in a sense to really relate it back to the original population model. But one could certainly do a branching Brownian motion model with just n particles. So what you would do is the branching rate would be inhomogeneous, and then you would just kill a randomly chosen particle at the time of the branching event. So there you would keep the number of particles fixed at n without making jumps in the fitness space. So that would be a way to do that. Could you do jumps in the fitness space without a population of, without a fixed population size? Yeah, you could certainly do that as well. So yes, you could do, you could make one of those adjustments without the other.
Okay. So I was trying to connect with the second model to what we've seen about pulled and pushed fronts. So so is there a front interpretation as a pulled front, presumably, because there is Bolthausen-Schnittmann, and where is the location of the front? Is it like near the rightmost, or is it further inside? And
yeah. So this would be, I think, what we would be calling a pulled front, and so you basically have this traveling wave, like I drew the simple little picture in the last lecture, and the shape of the traveling wave basically looks Gaussian, but it looks a little bit asymmetric and airy-like on the tails. And the place where it's being pulled, I would say, is at this location L, because that's where, when a particle gets a little bit beyond that, it has a big impact on the behavior of the process far into the future. So it's really within beta to the -1/3 of L that you're seeing that effect. Now, the one thing that's a little bit different from what we're used to in the BBM with absorption is that it sort of takes a while. So when an individual, when a particle gets out there to the right edge, and it's going to have a big effect on, it's going to create a big jump in the population size, it doesn't happen quickly on the time scale that we're looking at. The descendants of that particle sort of slowly move further to the left. And then after a time of order rho over beta, they're ready to get close to the origin. And all of a sudden, then the population size should explode.
okay, so could you then recall the time scales again? So
yeah, so I think the best picture to look at is this one here. Right. So the particle that's at y at time t is descended from the right edge at this earlier time. And so if you have at this time here, one of these events where a particle gets unusually far to the right, then it's going to take t of y units of time before you see a large number of particles concentrating around y. It takes a while for the particles to get over there.
Okay, and so maybe one last question. So is there again sine times exponential shape near the front, or
is there a sine times exponential shape? So basically that area function is playing the role of the sine, right? Where we used to have the sine, we now have the area function. So one can see that maybe best here in the formula for the density, right? There's e to the minus rho y times this times this area function. And what we're used to for the BBM with absorption would be to have a sine function there. And throughout the argument, that area function, you just sort of manipulate with that in the same way you would manipulate the sine function. So it's a little bit of a different shape for the fittest particles near the origin. They're described by that area function rather than the sine function.
Maybe one more this time.
And sorry. So thank you for it. So regarding the area function that appears in the front of this model with inhomogeneous branching, it reminds me the area functions that appear in the work of Maya and Zaitouni on time inhomogeneous branching Brownian motion. Is this just a coincidence, or could there be some connection between the two models?
I mean, I wouldn't rule out the possibility of a connection. I'm not aware of a direct connection at this time.
Well, let's thank Jason for this great lecture series again.